So you're familiar with a number of stable nuclei. When we take a look at the periodic table, we see that the atom of hydrogen typically has a single proton in it, and so its mass is roughly 1. When you take a look at carbon, then we're looking at typically carbon-12, which means it's got 6 protons and 6 neutrons. If you take a look at calcium, we're looking at typically 40 grams per mole on calcium, and so we're looking at about 20 protons of calcium and 20 neutrons in calcium. And so what we see early on in the periodic table is frequently a ratio of 1 to 1 when we're looking at neutrons versus protons. If I were to plot the number of protons here on the x-axis versus the number of neutrons on the y-axis, we initially start off such that the protons are equal to the neutrons or very close to that, and so we see a lot of nuclei which are stable right down here at the bottom of that graph. But it turns out that as you try and stick more and more nuclei into more and more protons into a nucleus, those protons begin to repel each other. And as they're repelling each other, they need something to kind of buffer that a little bit. And so that's where the neutron comes into play. So we start getting more and more neutrons as we get heavier and heavier nuclei. And so what we end up seeing actually is what's referred to as a band of stability. And we find that this band of stability kind of goes something like this, where all these nuclei are stable, sort of in this band. So if I were to take a look at that band, it would do something like this. It would go up like that, and it'd fall away from that 1-to-1 line that we see drawn in here. All right, so it starts off on that line, but then pretty soon falls off that line. So this is called the band of stability. The light atoms are stable in a 1-to-1 ratio. Heavier atoms require more neutrons. And this is all correlated to the binding energy, where we're looking at the energy in the nucleus. So when I take a look at another kind of graph, if I were to plot the binding energy, and this is binding energy per nucleon. So we calculated a binding energy for oxygen a little bit earlier, and we came up with 127 mega electron volts for an oxygen 16 nucleus. And so if I were to plot binding energy of the nucleon versus the mass number, right? So 127 mega electron volts, and that was for 16 nucleons, so 16 protons and neutrons together. That gives me a value of 7.94 mega electron volts per nucleon. That's for oxygen 16. It turns out that when I do this plot, what I get is something that looks like this. And right at the top of this graph, right here at this point, is iron 56. And that's at about 9 mega electron volts per nucleon. So oxygen is coming in at about 8, and so oxygen is sitting somewhere around here maybe, right? Helium is down below that, hydrogen is down below that, and so what we find is that the atoms to the left of iron 56 are all trying to get their nuclei to be more stable, and so these atoms tend to work towards iron 56. They combine their nuclei, and when you combine their nuclei, we call that fusion. Boy, that was pretty bad spelling. Let me try that again. Fusion. That's better. And the heavy elements like uranium and plutonium and things like that, they are working in this direction, and we call that fission. So in fission, you have the heavy nuclei splitting apart into smaller nuclei so that they can ultimately find themselves at iron 56. And this is the way that we typically then find the inner core of our planets as molten iron, because all of the elements are working to find themselves to become that most stable of nuclei, iron 56.